Non-photorealistic rendering is a rendering style that aims to purposely have unrealistic looks. While most graphics rendering aim to simulate and emulate reality as close as possible, non-photorealistic rendering diverts on purpose. This is usually done by having a high level of abstraction in a given illustration, or by limiting the details in the image. Research presented at SIGGRAPH by Saito and Tokichiro Takashi in the 1990s suggests that limiting the amount of detail in an illustration could alleviate confusion in the user. Many different styles and techniques exist under the umbrella of non-photorealistic rendering, but the one we will be working with is the one known as cell shading.
Cell shading, also known as tone shading, is a non-photorealistic shader that imitates a draw 2D comic book look, which basically divided to two parts. First is the first color changes on the object instead of changing smoothly. In tone shading, it would be a clear cut between different color region. Second, the tone shaded objects would normally have an outline, which conducted by the edge detection. This shader method was popularized in video games, and several game companies such as Gearbox and Tilted have art styles that learn heavily on cell shading. The popular method of implementation is heavy outlines around objects, along with bulky, non-mixed shadows, and the most examples shown in this video will be that on regard. There are a few principles from Edward Inroth in 1982 and Tom Patterson. That is the first, the shadow and the specular highlight should be omitted. Second one is the light source shoot from the top of the image, which is normally from the top left corner. The third one is the thickness of the outline should be response to the orientation of the object in the thing that the distance from the viewing camera. The fourth is the transition between ridges and the valley should be clear and sharp. The last one would be when use computer to generate a shaded effect image. The image should be based on a smooth and original geometric model.
In the game engine Unity 3D, the default toon shader has several drawbacks. First of all, no specular reflection can be seen on the default toon shader. Second of all, the metallic and opacity options cannot be used with the default shader. Third of all, the Unity toon shader works as a texture instead of a light effect. The last and biggest problem with the default toon shader is that the outline becomes larger the further away you zoom from the object. The reason for this is that the Unity algorithm copies the object and calculates all the normal vectors from the faces that can be seen from the camera, so the outline is expanded.
The first published algorithm of cell shading was introduced by Adam Lake and his team in year 2000. Their shading techniques finds a transition boundary and shades each side of the boundary with a solid color. The lighting equation used to calculate the diffuse lighting at the vertices for both smoothing shading and cartoon shading is shown in the equation number 1. In the algorithm, max light normal light vector dot n vector means the dot product of the normal vector of the surface and the light direction, and which gives the angle of the light hitting the surface. And if the max function is checked if the angle is above 0 or not. And if it's above 0, which means the light is hit on the surface, and if it's smaller 0, then the light won't be visible. The threshold of the program is to determine which part needs to be light up and which part should be as shadow, which is calculated by the angle of the light source and the normal vector. And the calculation is executed in each frame, the max value for each vertex, and use the final value as a texture coordinates for the pre-compute one-dimensional texture map. In 2003, DiCarlo introduced the suggestive contour. The figure on the left shows the outcome of the suggested contour techniques. The one on the left demonstrates the concept of these techniques. C as the mean viewpoint. In that case, the Q would be the contour. Moreover, the nearby viewpoint C dot and the Q dot would be the contour. The point P is the mixed area, depends on the viewing angle, which is from the C or C dot. For instance, viewing from the C, then the point P would be the suggestive contour, but the Q dot is not. By the definition of suggestive contour techniques, which needs to be located all the points which similar to the point P, in this case on the entire surface of this object. In year 2007, DiCarlo, based on his work from 2003, the suggestive contour, he developed the new technique which is called suggestive highlines, which has the same concept as the suggestive contour, but puts the highlight into the computation process as well. On the left is a figure which demonstrates the concept, and on the right is the outcome of the techniques, also the combination of different methods.
Pac-Man is one of the most iconic games of all time, and although it's not the perfect example of toon shading, it is an essential early example of the tight link between games, illustration art style, and animation. The cell shading got the name from hand-drawn animation cells. The 2D animated games like Pac-Man are not considered cell shading, which specifically refers to the stylized visual approach of 3D environment shading. There are more examples of this, like the Simpsons arcade game in 1991 and Earthworm Jim in 1994, both of which has pushed the development of cell shading further. The Jet Set Radio is the first game which technically used toon shading. At the time, computation powers of personal computers weren't as powerful and couldn't run photorealistic 3D games. So the game studio decided to solve this by taking a different approach and opting for a comic book-like style, which both turned out to use less processing power but also popularized the game. Another game to use cell shading would be Clover Studios' Okami, which simulates old Shinto iconography by emulating watercolors and a comic book-like look. Another comic book-inspired game is Platinum Games' Mad World, which uses cell shading to give it a sort of black and white noir comic book look. It is very similar to Frank Miller's 1991 Sin City comics. In Mad World, all grayscale is eliminated, and the very hyper-violent game is visualized in stark black and white, with the only color being shown red for blood. Lastly, Gearbox's Borderlands is a series that is very known for its cell shading-like look. However, they don't technically make use of a cell shader. Instead, what they have is handcrafted textures and a software that draws thick outlines on these textures. But they are very well known for looking a lot like cell shading.
Okay, now then we start to explaining the code. Here is all the code we have. We still always start with the name of the shader and the basic structure of the shader. We have the properties, sub-shader, and the shader itself start from here, the CG program. And of course we have this hashtag program vertex vert and the program fragment frag to represent the vertex shader and the fragment shader. And we also have the user specified properties and the struct and vertex output, vertex input, fragment output, fragment input, and so on. At the very beginning in the properties, we have the first one, the color. It's just define the color of the object, and we have the unlit color and lit color. It's just define which part, the part being lighted of the color and the color haven't been lighted, the shadowed part of the color. And also we have the outline color is just a black in our case, and the lit color is the outline which being highlighted have been light up the color. And also we have the unlit outline thickness as one of the properties. It's just the outline. When we switch the camera angle, the outline will change as well. And inside the subshader, we have text to initiate the light mode for inside the Unity. In our case, is ambient light. And inside the user-specified properties, we just use the uniform float for to define all the color and the unlight diffuse threshold, all those things. And inside the struct, the vertex input. First, we have the vertex position, which is which takes the position from the object into the vertex. and the flow-through normal, just trying to find all the normal vectors inside the vertices of the faces. And the structure vertex output, we just transpose the object to all the vertices so that Unity can read the information from there. And inside the vertex output part, we have two matrices. First one is a float 4x4 model matrix, which is the current model matrix, which transform the information from the object into Unity by matrix. And the Unity word object is just one function inside Unity. You need to use that one to call that function. And here we have the output of normal direction, and we normalize the dot product between the input normal and the mode matrix inverse information. And at the end we have dot xyz. Dot xyz just tells the Unity the position of this output information to x and y and z direction. And normalize function is just normalize all the value to in between 0 and 1. And here at the very end is just transfer all those information to transform the information to input and then return it to output. Then the fragment shader can read it and do further calculation.
Next, we move on to the fragment shader, which we see here. To begin with, we simply get the normal direction vector by normalizing the normal direction of the input, and we do the same to get the view direction. We normalize the world space camera position minus the input world space XYZ coordinates. Then we just initialize two variables and we start to check if there is any directional lighting. And if we find any directional lighting, we set the attenuation to be just 1, so there's no loss of intensity of light because directional light has no position. And then we get the light direction by normalizing our world space light positions coordinates. If there isn't any directional lighting, then we assume that there is either a point light or a spotlight. And then we get the vertex to light source vector, and we measure the distance of that, and then we set the attenuation to be in relation to that distance, so 1 divided by the distance. And then we store the light direction by normalizing the vertex to light source vector. Then further down, we go to simply just initializing our unlit color, and we check if our attenuation is above our diffuse threshold. And this is done simply by checking if the angle of the light hitting the surface is, well, first of all, if it's above 0, which means it'll be in front and not coming from the wrong side, so to speak. And then just checking if it's above that threshold of what we said earlier. And if it is, then we will change the color of the fragment to be the color chosen multiplied by the light color. Then we check the view angle, and we interpolate between our two outline thicknesses using the angle of light as the interpolation value. And if we find that this is above the angle of light, we set the pixel color to be the outline color multiplied by the light color. Then we move on to our outline. We calculate the angle of view, and then we do a linear interpolation between the view angle to get a certain part of our object to have the unlit outline thickness and a certain part of it to have the lit outline thickness. And we use the angle of light as the linear interpretation value. And then we simply use the light color and the outline color to get the fragment color. Lastly, we move on to checking whether or not the light is in front, and then we take our attenuation and times it by the reflected vector of the opposite light direction, and we check whether or not that's above 0.5. So we have more than half of our attenuation, is there more than half intensity? And if so, we simply set our fragment color to be mixed between the chosen color and the light color. And then we, of course, return it as a float 4. And here in Unity, we can see our results. On the left side, we have the shader we found from the online resource. And on the right side, we have the shader that Unity has natively. Already now, there's some clear differences. You can see these, this reflected light and the outline thickness is different. If we try to click in and look at some of the values on the material, between ours and the one provided by Unity, there's a lot more to tweak in the one we have. For example, lit and unlit outline thicknesses, colors and shininess, and so forth. However, on more complex objects, Unity's shader wins out by simply being very consistent, whereas you can see here the outline on complex objects becomes quite silly and ends up coloring a large amount of the object.